One is perlite, okay. Perlite. Perlite will happen at this point, exactly at 0.8% and 727 degrees Celsius is eutectoid point. At eutectoid point, perlite is formed. Below that, at any temperature at 0.8% carbon, you will having completely perlite. Below 727 degrees Celsius and 0.8% carbon, you should be having carbon. 0.8% carbon. You have completely perlite region. If you are moving or if you have carbon content less than 0.8, then you will have two phases. One will be alpha and one will be perlite. But if you are having carbon concentration more than 0.8, you will be having Fe3C and perlite. Okay, what is perlite? Basically, if you see the microstructure, you will see like this. Sum of the part, it's a lamellar structure. Means suppose first alpha iron will come, then if Fe3C will come, again alpha iron, then Fe3C, then alpha iron, Fe3C, like that. That is called lamellar structure. Suppose I am treating this as alpha. Okay, alpha means ferrite iron. Okay, suppose this is Fe3C. Then again we are having alpha. Then this is again Fe3C. Then we are again alpha. Then again Fe3C. Again we are having alpha. Like that. Okay. So like that, in that sequence, this is called perlite. Just a microstructure, simple microstructure, what we can say. This is Fe3C. So it is a mixture. It is basically a mixture of alpha and Fe3C. Remember, and that is a lamellar structure. So this is all about the perlite. And you might be thinking or might be confused that it is the softest phase in the iron carbon diagram. No, it is not the softest phase, because perlite has the properties of alpha as well as Fe3C is a mixture. So since Fe3C has a lot of carbon, 6.67% carbon, that is the maximum carbon that can be present in any component. So since it has a high percentage of carbon, so it is very brittle. I will discuss the property of this. It is brittle and it is very hard. So its hardness, when combined with alpha means ferrite iron, it will enhance the hardness of the perlite. So that's, in that case, perlite will not be the softest phase. Alpha is the softest phase in the iron carbon diagram. Remember. Burite. Lady burite. What is lady burite? Lady burite is found at this point, okay? Below this temperature. What is this temperature? Below 1148 degrees Celsius, and this is 4.33% of carbon. At exactly 4.33% of carbon, if you start moving like this till here, in this region you will have only lady burite. Lady burite is basically the mixture of gamma plus Fe3C. So it is again a lamellar structure. What I have done, suppose this is this is gamma, then this will be Fe3C, then this will be gamma, this is Fe3C, gamma, Fe3C, gamma, Fe3C. gamma. This will be Fe3C. This will be gamma. This will be Fe3C. This will be gamma. Fe3C. Fe3C. This will be again gamma. Like that. So this is just a simple microstructure of ladybulite. It's a lamellar mixture of gamma. Gamma means austenite iron, and ferrite means Fe3C, cementite. Now coming to Fe3C, okay? Fe3C. So first I would like to say some of the properties. It is very brittle, okay? Brittle. Very brittle and hard also. Why? Because the carbon percentage is very high, okay? It is hard and brittle. Less tensile strength. Tensile strength is low. And high compressive strength. High compressive strength. High compressive strength, okay? These are the properties. Then the structure of cementite is actually called BCO, body centered orthorhombic BCO structure. If you want to know what is orthorhombic crystal structure, please mention us in the comment box. This is body centered orthorhombic, and it is very hard and brittle. It is a mixture of iron and carbon. But remember, carbon content is always 6.67% by weight. 6.67% of carbon should always be present in the iron. Then that interstitial compound is called Fe3C, means cementite. Cementite, it's called cementite, okay? It's called cementite. So this is all about the cementite. Now let us see more what we can, though those things doesn't appear in the iron carbon diagram. This is just the end of iron carbon diagram, but still I like to add some of the more phases what we can see, but they are not equilibrium phases, okay? You will not see these things, martensite. You will never see martensite in the iron carbon diagram. But still I would like to explain what is martensite. Martensite is basically the hardest form. It is the hardest form of iron among all equilibrium and non-equilibrium phases. Hardest form of iron among all the equilibrium and non-equilibrium phases. This is the martensite, okay? Martensite is not formed just by itself. Like martensite is formed when you are cooling austenite iron, on cooling austenite iron above critical cooling rate, there is a specified rate. If you are cooling above that rate, then the austenite iron will change into martensite. One more thing I like to say, its structure. In several exams they used to ask, the structure is BCT, body centered tetragonal, body centered. Body centered tetragonal, BCT, crystal structure. BCT crystal structure. This is about the martensite, okay? So, if you want to know what is body centered tetragonal, please mention us in the comment box. We will make a video on that also. So this is about the martensite, and it is, remember, this is the hardest form of iron what you can see, because it is being cooled at a very faster rate, and when you cool the something at a very fast rate, then the number of dislocations will be very high and the hardness will be very, very high. Okay. This is non-equilibrium phase, and that is a metastable compound. Martensite is not a stable compound. Martensite is basically a metastable compound. It can change its phase up depending on temperature. On one temperature, if you are having room temperature, you will get martensite. But if you are changing the temperature, the martensite will disappear and it will change into maybe in austenite or some other form. There is one more thing, benite, B-I-N-I-T. This is also a hard form of iron. It is not the hardest, but harder than pearlite or something like that. Less hard or hardness is less compared to martensite. This is also formed from austenite. When we are cooling austenite at a rate that is lower than the critical cooling rate, but higher than what we can form pearlite. So at that cooling rate, if you are having this, the cooling rate is more than the cooling rate what we require for pearlite, and it is less than the critical cooling rate, in that case benite will be formed. Remember, cooling rate is higher as of required for pearlite formation. So this is about the benite. Remember, this is not an interstitial. This is an interstitial of a compound, but this is not lamellar. It is not having a lamellar structure. There are one more phase called trustite. Trustite is there, and then sorbite is there. These are also non-equilibrium phases. They are not equilibrium phases. They are not appeared in the iron carbon diagram. They are found on very on cooling at a very high rate. It is formed at a moderate moderate, during moderate stage of tempering. Lower temperature stage of tempering. Tempering will get survived. Tempering is a process that we see in heat treatment. If you want to know about tempering, please mention us in the comment box. We will provide the video on that also. So this is all about the iron carbon diagram, what I can tell from my view. So the questions will be mostly on this, maybe steel percentage they will ask, the cast iron percentage they can ask. Then they can ask these 3 points, these invariant points. Then they might be keen to know the temperatures. Remember, and one more thing I like to say, if you are having pure iron, the melting point is this is 100% iron, okay. This is 0% carbon for 100% iron, Fe. This is 0% carbon. This point is 0% carbon, but 100% Fe. This point is 6.67% of carbon. So if you are moving in this direction, then in that case the percentage of iron will decrease and the percentage of carbon will increase in the mixture. So you can see at 1538 degrees Celsius, if you go above this temperature, 1538 degrees Celsius, if you go above this temperature, in that case 538 degrees Celsius, you will find only iron in the liquid form. So this is the melting point of pure iron. And one more thing, if you are moving in this way, start moving in this way. If you move just above 912 degrees Celsius, you will see all the alpha iron get converted into gamma iron. So alpha changes into gamma at 912 degrees Celsius. At 912 degrees Celsius, alpha changes into gamma iron. Again, if you move in this way, you can see just above 1394 degrees Celsius. If you are moving above this 1394 degrees Celsius, all the gamma will change into delta. So at 1394 degrees Celsius, gamma changes into delta. Okay, so you need to remember these three temperatures: 1538 degrees Celsius, 912 degrees Celsius, and 1394 degrees Celsius. These are the important temperatures. These are all the important temperatures. 1148 degrees Celsius, 1394. These are very important. You need to remember these temperatures. So this is all about the iron carbon diagram. Still you have any doubt, or you feel like you need some clear explanation, please mention us in the comment box. Okay friends.